Welcome to the last session of PEPM 2022. In this session, we have two contributed talks. The first speaker is Chris here. He's going to tell us about how to use dependent types to prevent attacks. So please start your presentation.
Great, thank you very much. Okay, so this talk has kind of come out of an ongoing EU project that we've been running at St Andrews called Team Play, and that's what basically all these logos are on my slides. So this finished in the summer last year, and it was a 3.5 year project. And one of the things we were looking at very closely on that project was security, and particularly why security is important for software developers, and how we can build new techniques and tools to kind of help software developers write secure code much more easily. So this was one of the goals of the project, and kind of resulted in this paper. And what I'm going to be talking about today is very specifically sidechannel attacks, which is one specific type of security problem. And the idea behind it is, if you've got a bit of code like the one here on the right on the slide, if you go all the way down to about line 14 here, I've got a conditional on a function that's using a secret variable. So we can imagine k here is some secret key, and bit ki is the ith bit of the key. Okay, so I'm checking the ith bit of the secret key is equal to 1, and if so, I'm going to do a computation beneath it. So this particular example is a modular exponentiation. It's very typical of the type of algorithms you see in RSA programs. It's also indicative of kind of iterative conditional branching generally. Here, this computation a times x will only be computed if the bit ki is equal to 1, and it won't be computed if it's not. And this is a security problem, because if you are an attacker monitoring the system that this software is running on, you can do very simple things to figure out what the value of the secret variable is. And even just doing simple things like calculating the Hamming weight of k, and the Hamming weight, for example, is the number of ones that occur in k. And we can by using a Hamming weight and also analyzing the power draw of the system while it's running the software, you can basically figure out what the key is exactly. So, for example, if we're looking at the power draw of the machine, when we're doing this computation here, the power draw will increase and so on, and then we can figure out that we can use that to kind of backward engineer the Hamming weight of the key, and then we can get to the key itself. So this is security flaw. So what I'm going to introduce in this talk is a technique that is programmer driven, so a technique based on rewriting dependent types and refactoring that can convert or transform a program that has this security flaw property into one that doesn't. So we eradicate the security problem, but we do it in a completely automated way. And it's going to use a technique called a semi-interleaved ladder. And this technique comes from the literature. It's sometimes known as a Montgomery ladder in the security domain. The semi-interleaved ladder is a specialized version of a Montgomery ladder. And in its general sense, what we're looking at is something like this on the left, where we have some kind of conditional over some secret variable, and we have some functions in the program that are defined, and we're going to convert it into a balanced version of it, where we have a conditional with both if and else versions, where we kind of exhibit equivalent computations in both branches. But the idea is that if the bit is 1, we do the computation as normal, but if it's 0, we do some kind of equivalent counter computation that takes an equivalent amount of time and power. And by doing this, it means that an attacker cannot know when we're in the conditional branch and when we're not, because both branches exhibit the same non-functional behavior. So this is kind of the general idea. And to go into a little bit more detail, we're going to use something called the semi-interleaved ladder, which I've mentioned. There's already some theory built up on ladders and Montgomery ladders in the literature that we've kind of used as to kind of start with. So we start with the point where we have two functions, an epsilon and lambda. We know what these are. So these are defined somewhere in the program. And there are three equations, equations 4, 5, and 6. So actually another three equations that come before this that we're not going to use for a different type of ladder, which we discussed in the paper. But for the purpose of the talk, we've got equations 4, 5, and 6. And they state various properties. So for example, this one, epsilon lambda applied to x, has to be equivalent to lambda applied to epsilon of x, and so on. So we have to, when we're going to rewrite this program, refactor it, we have to ensure that these equations hold. The other thing that we need to introduce into our code is this function f. So we know epsilon and lambda, so we know what the epsilon is here, and we know what lambda is. So we have these in the program already, they're defined, but we don't have an f. And we need to generate an f and then transform the program so that we call f like this, such that these three equations still hold. And this is one of the things that we have to do as part of the transformation. And that's what we're going to use the dependent types for underneath. So we're going to use one technique called refactoring. I think everybody nowadays knows what refactoring is, but just as a reminder, this is a technique that transforms the structure of the program's source code, but without breaking its behavior, so without changing its behavior. And we have embedded our refactoring tool into Eclipse. So we have an Eclipse-driven tool that allows the user to go from this unsecure version of their code into a fully semi-interleaved ladder version. And underneath the Eclipse engine, the Eclipse front end, we have an engine underneath that's implemented entirely using Idris. For those of you not aware of Idris, it's a dependently typed functional programming language. It's similar to Agda a little bit. It has a slightly more emphasis on building runnable programs rather than just proofs. So you can use it to write proofs and also runnable programs. It was developed by Edwin Brady, who's a colleague of mine at St. Andrews. So it makes sense for us to use Idris here. It's very nice way to write proofs, because what you do is you define a type to express the property you want to prove. The inhabitants of the types become the proofs, and the type system acts as a kind of a theorem prover, and the program becomes the proof object of the theorem prover. So I've got some examples of the types that we use later in the talk. One thing to say is we're not doing this for the whole of C yet, and that's the next step. But what we're doing is we're taking a tractable subset of C in order to demonstrate the principle of the approach that we're showing. And we're taking a small arithmetic expression language to build upon. So, for example, we have literals, variables, simple arithmetic expressions like addition, multiplication, and so on. And we have a semantics underneath that's based on the well-known theory of abelian rings. So this gives us properties of addition, multiplication, things like associativity, transitivity, commutativity, and so on. And we have all of this implemented in Idris as a provable semantics. So we have general soundness properties of all of these semantics and proofs thereof in the implementation. Building it on the semantics with the soundness properties is what we need to do, because we need to ensure ultimately that the refactorings are going to preserve the semantics of the code. And although we don't have a full semantics of C, it does give us a strong confidence that the refactorings are correct. So having semantics and then building the soundness against those semantics is very important. And this is all done using dependent types underneath. So we also have an abstract interpretation. So we're starting with C. So we need to get from C to Idris. So we have a semantic representation, and we have a way to convert the C program and convert it into our arithmetic interpretation. There's just an example of how we do that. So we generate some abstract interpretation and feed it to Idris underneath. So I said to you at the start of the talk that we assume that some functions exist within the C program. So the developer starts with a C program that they've developed, and they identify within the code. In fact, I have an example of this later. They identify within the code the epsilon component and the lambda component, and then they give that through Eclipse, and Eclipse gives that to Idris, and it generates some abstract interpretation of the C program, including the epsilon and the lambda functions. And what it does is it converts it into our Idris representation, so then we can start rewriting it and finding the F and also providing proofs that all of these equations are going to be met. So we do this by using rewritings underneath, by using types that express relations of rewritings. So for example, here's just some examples of some of the relations that we have in Idris. So for example, an A rewrite is an arithmetic rewrite that forms a relation between E and F. So we can rewrite E into F, basically. We also have like bidirectional rewrites. So we can rewrite E into F, F into E, and so on. And we can build this up into a kind of a theory, sound theory of rewriting. So here's an example here. Using the types, for example, we can show that we have an equivalence relation between some X and some Y. So if I have some E and some F, and I can rewrite E into F, and I can also kind of denote E into X. So I have a semantics. So X is a kind of the denoted representation of E. Y is the denoted representation of F. And I can rewrite E into F. Then I can also show that X is equivalent to Y as well. So this is kind of how we build up these rewriting proofs as we go. So we have lots of these rewritings underneath, and what the Idris engine does is it basically searches for rewriting. So it employs lots of rules. We start with an arithmetic expression. Because it's all built on a theory of abelian rings, we have very well-defined and understood rules that we can rewrite, and we simply keep applying these. So here's just some examples. So example squaring, E squared can be at E times E. This is very trivial. Commutativity of plus and multiplication, associativity, and so on. There's a lot more rules underneath the hood, but these are just a few to give you a kind of a feeling of what's going on. And what we want to do is we want to find a rewriting where we can rewrite some X into some Y, but that is still observing the same expression semantically. So the semantics of X are still equivalent to the semantics of Y. And we do this, this is really a constraints problem, not a types problem, finding the rewriting. So the types fit very well with the soundness proofs, but really finding the rewriting is a constraint problem, really. And you've got to be careful that you don't just arbitrarily apply rewritings after rewritings, because you'll just end up in infinite streams of rewritings, or you won't get any progression in the rewriting. So you'll just keep rewriting, but you won't progress towards finding that F, which is what we wanted to do. So what we do, just as a kind of a way to demonstrate that we can do to find rewritings, we use a taboo search, which is basically like a breadth first search. So we start with an expression, we rewrite it, and we do this in a breadth first search manner. So we then go into we rewrite it, we go into its children, we write each child, and so on. And what we do is we have a taboo list. So if we've seen the rewriting before, or the rewriting doesn't make progress towards our goal, we add it to a taboo list to ensure that we don't keep repeating it. And we have a depth, that we have a default value that we set the depth to, and we keep searching until the depth is hit, or we find what we're looking for. So the way we find proofs in Idris, this is just an example of one of the functions. So this is our discovery function. And the way it works is, if I just go through this in turn, each of these parts of the type correspond to proofs of the equations that I showed at the start of the talk. So example, this component here, the rewriting here, corresponds to the equation where we have an epsilon lambda x, and we can rewrite it into a lambda epsilon. And we use our type rewrite to show the relation between these two terms. Then we can also, for example, we can find some f as well, such that we can show the rewriting between lambda epsilon x and lambda x, and also that our lambda x is within f as well, which is also a property of one of the equations here. So subterm here is another type where we can give a proof that this term here, lambda x, actually does exist. It occurs as a subterm within f, and that's an important part of the proof. The last equation, where we have f of lambda x and x is equal to lambda epsilon x. This is kind of the reverse of the previous equation, where we have the previous equation where we have f of x lambda x. So we do this by a special type called EQ6, where we relate some f to some special f prime, and we can find an f prime such that we satisfy this proof. which I'll explain now. So proving equation 6, well, the way we do this is we have to prove that f of lambda x of x is equal to lambda, the formatting has gone a bit strange here, but it's basically this rule here. F of lambda x of x is equivalent to lambda epsilon of x. And what we do is, because we already have a proof of equation 5, which gives the opposite, we can basically simultaneously substitute all the lambda x's in f for x, and then all occurrences of x, f of lambda x, and we can substitute these, and then we can get a proof of this equation. And we do this by this type, and we use a special relation here to prove that this LMT gives us a relation that allows us to prove that, for example, this term lam not only occurs in f, but the proof tells you the position that it occurs in the term. And we can use this to build the proof. So if we know the position that, for example, lambda occurs in f, we know the position that x occurs in some f prime, and that these positions are the same, and that x occurs in f and lambda occurs in f prime in the same positions, and we can rewrite f into f prime, then we have a proof of this equation. So this is how we basically do the proofs. And we can do proofs of positions in the standard way, so it's just a kind of a basic extension to the normal LM proof in Idris. And so we can use this to form proofs, for example, that T occurs within G, but also the positions that it occurs within, in order to get the proof out. Then we can put it all together to get these equations 4, 5, and 6. So we use more Idris plumbing to kind of put these proofs together. And this allows us to basically apply this then to a program. And to go through an example, here I've got an example square and multiply. So we go down here to line 10, I've got a function exp sn. And then within that on line 14, there's a conditional here, bit ki is equal to 1. And if it is, then I'm going to do this computation on line 15. So this is very similar to the example that I showed at the start of the talk. So we run this through the refactoring tool. The first thing we need to do is we identify what the epsilon and the lambda functions are. This is actually quite simple, because we have the template for the ladder, the semi-interleaved ladder. The epsilon and the lambda have to occur precisely in these positions within the code, in our instance. So we can simply use a function extraction refactoring to get these out. So this is very simple. So we simply just extract these into functions. So x squared here becomes epsilon, x times a here becomes lambda, and then we just simply replace them with calls to the function. So this is a simple transformation. And then once we've got the code into this kind of format where we have epsilon and lambda, then the programmer can simply highlight this loop in Eclipse, and then choose ladderisation within the menu of Eclipse. Then it becomes automated. We give it to Idris automatically. Idris performs the rewritings. It finds an f and it forms the proofs, and that all the equations are met. And then what it does is it generates a new C program like the one you see on the right, and then Eclipse renders it to the user. So here we're going to what it does is it refactors the code on the left into the one on the right. And you can see here it's introduced some function f. This is just the function f will be a unique name. Here I'm just calling it f just for the purposes of the demonstration here. We can see here f is x times y, and then what we do is we actually introduce two if statements here, one for the true case, where x is going to be calling f, and then y is calling epsilon, and then one for the false case, where we call f and epsilon again, but we kind of revert or invert the way we assign to y and x. And the reason we don't put an else here is because actually compilers can actually optimize if and else is out. So the way compilers typically work is in an else, it will just jump to the else if it's false, which gives a little bit more of an overhead in the timing metrics. So what we actually had to do is to insert two if statements, one for the false and one for the true branch, to avoid this problem. So this is an example of what Idris gives back. The programmer doesn't actually see this. They don't need to see this. All they do is drive Eclipse, and then it kind of communicates with Idris automatically, and the engine just gets on and does its job. But this is an example of what Idris generates. So the top bit here if you can kind of decipher through the code here, this kind of abstract syntax tree here, this is the f that Idris has generated, so it's found this f, such that all these equations hold. And it gives proofs as well of the equation. So here, for example, is equation 4, where epsilon lambda x is equal to lambda lambda epsilon x, and then it shows the proof of why that's true as part of its output. So here, for example, we have the rule squares multiply, then we have associativity, then congruence, associativity, and then so on. And the same for this equation, f of x lambda x is equal to lambda epsilon x, and again, we can prove it via the steps here. And then proof of equation 6 as well comes here, where you can see here we have make equation 6, which then forms the proofs of the positions and so on to get the proof out. And I don't know why the formatting on the slides there has gone a bit strange, but it shouldn't matter too much. So I'm just going to finish here with just showing you some examples and some of the timing metrics. So here's one example with the modular exponentiation. So here we go from this example here, where we have a conditional here on k. This is slightly different. We don't have a function bit, but we are doing some bit manipulation on k to figure out whether the ith bit is 1 here. And if it is, we do some computation on it. And this gets converted automatically by our tool into the code here at the bottom. And so here we've introduced an x and a y branch. Here we don't have the f, we simply inline the f here. So rather than calling f, we just simply inlined it, just to remove the overhead of it having to call a function. And you can see here, the graph here shows that the red line here was the unrefactored version. And as you can see here, if you read the graph here, going along the bottom here on the x-axis, this is the number of Hamming weights. So this is the number of bits of 1 bits within the key. And the y-axis here is the execution time. So as you're uncovering more bits within the key, the execution time increases. So you can use this to basically decipher what the key is. In our version here, we get a constant time, like right across the board. So there's no way an attacker can use this constant time to reverse engineer what the key is from the execution. Another example, modular multiplication. So it's a very similar kind of example here. And again, we have a conditional branch here on k, and we have some computation over it, and then we refactor it into the code below. And again, the f is introduced, but then we inline it completely. So here the f is x plus y and y plus x here. And this is generated by Idris completely automatically. And again, we get a similar result. So we get a completely balanced constant timing for the execution and across all the branches. But very similar to the other example, as the Hamming weights increase, also the execution time increases in the unrefactored version, which would lead to a security risk. So just to summarize, so part of what we were trying to address was the idea that security is a neglected goal amongst developers. And the problem with this is writing code with security in mind is very challenging, really, for the average developer. Most average developers probably don't have the skill set to really make secure applications. So we wanted to start addressing this by producing tools, not only just tool support, but a full tool supported methodology for them. So they have refactoring, they have the rewriting, they have the correctness, the soundness results as well, all embedded within a framework. They use it as part of their normal IDE development process. They click a button, they go from a non-secured version into a secured version almost seamlessly. And with semi-automatic, because the user still does have to drive it a little bit, they have to tell the tool which part of the code they want to refactor and so on. But all of the engine rewriting underneath is done completely automatically. There's still a lot of future work to address. Obviously, this is we've looked at a small arithmetic language. It would be nice if we looked at the full semantics of C. This is obviously quite laborious, challenging work, but I think it would be interesting to do that. We could also look at more full generalized cases of this, so not just looking at if, then else, not just looking at if then conditional cases, but also if then else. So the fully generalized interleaved ladder, rather than just semi-interleaved ladders. Also, general soundness proofs of the refactorings themselves. I mean, we do have general soundness proofs of the arithmetic semantics, rewritings, but not of the C transformation. So that would be very interesting too. But also looking at other security properties too. So sidechannel attacks is just one type of problem, but also maybe fault injection attacks, maybe trying to think about kind of security patterns or anti-patterns in general. I call them anti-patterns because you think about it as being, this is an unsecured bit of code, so it's an anti-pattern. And then it's dual, what is the patternized version of that, the secured version of that? And how can we refactor from one into the other in a more general way? So I think that's all my time used up. So thank you very much for listening. And I really apologize for being slightly over time at the start. So thank you.
Yeah. Thank you, Chris. So if you have any questions, please post in the Q&A tab. Okay, I see a question. Let me show this on stage. So should we be worried that a clever compiler might optimize away your carefully generated rewrites?
Well, yes. Well, the answer is yes and no. So one of the reasons we had to do, for example, put in 2 if statements was because the compiler was doing exactly that. It was optimizing away the transformation we were putting in some senses, and leaving more vulnerabilities. So we had to get around that by putting in 2 if statements. Basically, it could be, the answer is basically, it's probably better that this would be embedded into a compiler, perhaps. So although we're showing the technique here, it would be nice if it was maybe embedded into a compiler rather than a separate system. So the compiler actually understood the optimization. And I think this is doable now, because rather than maybe using the Eclipse framework, we could have, for example, used LLVM or something like this to embed it within. And then the compiler kind of understands what refactoring we've applied and knows not to kind of touch it. There's other things you can do too, like the refactoring could maybe put pragmas around the code and tell the compiler, don't touch this kind of refactored bit of code, etc. But this is a good question. This is an important question, I think, to really think about very deeply going forward with this kind of work. So yes, it's kind of half answered, sorry, but we are very much aware of it.
Okay. Thank you. So I have a question. So how hard is it to support a realistic subset of C?
The answer is not really in how hard it is. I think we kind of know how to do it. It's more the effort.
Mm-hmm.
So I mean I've worked in refactoring for many years, and I've done soundless proofs of refactoring over big languages. Like, for example, Haskell, I worked on that for a long time, proving soundless properties of refactorings just for Haskell, even in the small version of Haskell, is a huge undertaking. Mm-hmm. I think for C it would probably be even larger, because of the semantics of C are much more messier than, for example, Haskell. But people have done it. Like, for example, there's CompCert and compilers like that, which try to verify the whole semantics of C. And I think we know how to do it now. I think it's a case of just putting the effort in to do it. Mm-hmm. I think it'd be really interesting. In fact, kind of the project that I want to work on is just refactoring C and showing the proofs of the refactorings, even if they're just simple refactoring. I think that would be a good place to start, and then maybe looking at more complicated ones going ahead. So, yes.
Yeah, sounds interesting. Yeah. Okay, so let's thank the speaker again. Thank you, Chris.
Thank you.